Okay, the next talk is titled Augmented Lagrangian Method for Online Game Theoretic Planning with Constraints. The speaker is Max Schwager, professor at Stanford University. He was an earlier professor at Boston University, and his education is from MIT, if I'm correct.
Yep.
And it's a pleasure to have you here. Looking forward to hear what you have to tell us.
Great, thank you. Thanks, Severio, and thanks to all the organizers for inviting me to give a talk at this workshop, or I should say the tutorial. Yeah, I'm really glad that that you guys decided to organize this tutorial because I think it's really the perfect time. I feel like there's a real explosion of research in game theoretic ideas applied to motion planning for robots. I think it's a very powerful paradigm. So I'm happy to be here to talk about some of my recent work on this area. So I'll be talking about augmented Lagrangian methods for online game theoretic planning with constraints. So the key of this talk is that we're looking at Nash equilibria, where the players all have constraints, hard constraints. And that makes things a little bit tricky, and it's also especially important in robotics. So let me start off with some motivation. So you all are probably familiar with human piloted drone racing. This is an example of such a drone race. This is a kind of a sport that's growing in popularity. This is really my main, or at least my initial motivation for getting involved in game theoretic motion planning. I find this just remarkable what human pilots can do. So this is a human pilot's flying only from this video feed. And you're seeing two really extraordinary feats. One is that the pilot is able to deal with the complex dynamics of the drone and fly through the track at very high speeds with very high accelerations, right? So this incredible motion planning, online motion planning feat. But there's another layer here that I think is really fascinating, which is the ability for the human player to compete against the other pilots. So there's a theory of mind happening where the human pilot is predicting what the other pilots are planning to do and trying to strategize with respect to those predictions. And it's not purely prediction, it's a coupled prediction. There's a sort of thought process in the pilot's mind about if I do this, the competitor will do this, and I would like to somehow maneuver to gain advantage. So upon realizing the kind of complexity involved in this problem, we started working on this specifically applied to drone racing in my lab. And here's an example from a paper, Transactions on Robotics paper came out last year, where we used an algorithm called iterative best response. We actually had to modify that algorithm. I'll talk about this in a second, to work with problems with constraints. And you can see here we have two drones. They're planning their trajectories in an MPC kind of fashion. And one of them is using traditional MPC, the other one is using a game theoretic planner. And we found that it's just a remarkable difference when you account for game theoretic interactions. You end up with a far more intelligent and competent racing vehicle. You end up really dominating the races with respect to a more traditional MPC approach. So let me dive in. This being a tutorial, I've really tried to focus on some of the technical details here. So we're going to dive straight into posing the problem. What do I mean by a generalized Nash style game? So I think you have all heard earlier in the talk about various notions of game theoretic equilibria, Stackelberg equilibria, Nash equilibria, and so on. So in a Nash style, generalized Nash style game, we have a Nash style equilibria that we're interested in. So every agent I has some objective J and some decision variables theta sub I. And this objective is also a function of the other player's decision variables. So we'll say our decision variables are theta sub I, all the other robots' decision variables are theta sub minus I. I think it's a fairly standard notation. Now, what makes this a generalized Nash style game is that there are also constraints. So every robot I has some set of constraints G, which also depend on its own decision variables and its competitor's decision variables. And we require that these constraints are met in a feasible solution. So the definition of the generalized Nash style equilibrium follows immediately if you're already familiar with what a Nash equilibrium is. So the definition is that at a Nash equilibrium, if you hold all the other robots' decision variables constant, then robots I's decision variables must be a minimizer of its own objective function and must satisfy the constraints. And this has to be true for all the decision variables at once. So in layman's terms, this just means that no player, no robot can unilaterally improve its objective. They're all kind of locked in a minimum. with respect to their own optimization problems. So this is a hard problem to solve. And what we're trying to do, so one might be interested in solving this in lots of different ways, especially in online motion planning. So you could solve for a policy, a Nash equilibrium in policies. Actually, what we're looking for here is a Nash equilibrium in trajectories. So we're going to have an open loop control trajectory, just control inputs as a function of time. And we want those control inputs for ourselves and for the other players to satisfy the conditions of generalized Nash equilibrium. And then the idea is that we want an algorithm that's fast enough that we can keep resolving this online, and then we'll get feedback in the MPC sense. So we'll be able to resolve quick enough that there is a notion of feedback involved. So let me talk about a standard algorithm, some standard class of algorithms for solving for Nash style games. It's called iterative best response. I suppose this has probably already been discussed earlier in the workshop. Now, the main content of my talk is not iterative best response. This is just purely for illustration because it's a simple algorithm. My claim is that iterative best response actually fails terribly in generalized Nash style games. So here's iterative best response. So suppose the ego robot, that the one that we're interested in planning for is the gray one. So let's suppose that we start with some arbitrary trajectory for the green robot. Maybe this is inherited from a previous time step. And then the gray robot plans the best response, assuming that the green robot has a fixed trajectory. And then the gray robot now plans for the green robot, simulates what the green robot will do in response to this gray robot's trajectory, assuming that this is fixed. And we iterate this way. So the gray robot is both planning for itself, assuming fixed green robot trajectories, and the gray robot is planning sort of to simulate what the green robot will do, assuming the gray robot's trajectories are fixed. This is iterative best response. So in a standard Nash style game, the Nash equilibrium is a fixed point of this best response map. This is called the best response map, right? So every robot is trying to find the best response to the other one. If this algorithm converges, it converges to a Nash equilibrium. So that's great. Problem is, in practice, it doesn't work at all with constraints. Why is this? Well, imagine that the green robot, we have a trajectory already set for the green robot, right? That means the green robot has the luxury of planning without regard to the gray robot's trajectory. That means it can plan disregarding its constraints because the gray robot it knows the gray robot will have to satisfy those constraints. So now when the gray robot goes to plan at the next iteration, it must satisfy the constraints with the green robot's trajectory fixed. And so it's at a terrible disadvantage, right? So whoever goes first in a generalized Nash style game, in a game with constraints, gets a huge advantage in iterative best response. And you end up with terribly lopsided equilibria, which favor one player or the other. And you also end up with large swings from one time iteration to the other. So this simply doesn't work. We, in previous work, have looked at modifying iterative best response. We have a version called sensitivity enhanced iterative best response, where we try to essentially allow for a constraint violation temporarily by imagining that through multiple iterations, all the constraints will be satisfied. And it works, but we'll show soon that it doesn't work as well as the algorithm I'm going to present today. So the algorithm I'd like to focus on is called AllGames. It stands for Augmented Lagrangian Game Theoretic Solver. It was published originally at RSS 2020, so about a year ago. And right now we're working on the long form journal version. It's under review for autonomous robots, but you can see the citations below. You can find the long form version on arXiv. So this work is really primarily the work of my PhD student, Simon Lecleach, who I believe is here in the audience. He's really the technical expert. So he can answer if you have any really detailed technical questions. I'm sure he's willing to answer those and correct me wherever I happen to go astray in this talk. This is also joint work with my friend and collaborator, Zach Manchester from Carnegie Mellon, who's an expert in motion planning. So, right, so let's talk first at a high level about AllGames, and then I'll really dig into the details of how AllGames deals with these generalized Nash equilibrium style games. So the high level idea is that we're going to deal with these constraints through an augmented Lagrangian. So we're going to append the constraints to the original objective function to end up with an unconstrained optimization. Similarly to how a normal Lagrangian is used to deal with constraints, but this is a slightly different concept than augmented Lagrangian. Well, I'll talk about the details later. And then we essentially do root finding on the gradient of this augmented Lagrangian. So we're talking about a second order Newton's method style algorithm where we just search for the critical points where the gradient of the augmented Lagrangian with respect to the decision variables is 0. Now, there's lots of details under the hood, so that's what I'm going to talk about. What's important is that this solves really fast, so much faster than IBR in our experience and much faster than other existing techniques. This can solve for a 2-player game involving autonomous driving in about 14 milliseconds per iteration. So we can easily, at 60, 70, 80 hertz, solve this in an MPC fashion to get reactive policies. So let's talk a little bit more about just the results of all games and the need for game theoretic planning in scenarios beyond drone racing. I talked about drone racing, fine, that's fun. But in practice, there are game theoretic interactions happening all around us. Humans are experts at negotiating with one another through motion and through sort of small iterations to arrive at an equilibrium that everybody's happy with. This happens all the time in autonomous driving. If you imagine merging on the freeway, especially when there's traffic, you as the driver merging onto the freeway are constantly calculating what the other cars are likely to do in response to your presence. And they are doing the same about you. And eventually you find an equilibrium that allows you to merge into the freeway. Now, this reasoning, this game theoretic reasoning, doesn't exist in current autonomous driving policies, which rely mostly on MPC style MPC style motion planning. And in this case, you end up with what's called the frozen robot problem. This is a very common problem in autonomous driving. We see this actually relatively frequently around Stanford and the Silicon Valley, where you have Waymo vehicles and other vehicles that are driving autonomously. They frequently get stuck when on the on-ramp when trying to join traffic on the freeway. And that's because they can't reason about the fact that the other cars will yield and open up a spot for them. So you see that here in a kind of toy simulation. We have 3 cars moving along kind of in a convoy, and then the yellow car is trying to merge. And the yellow car has to stop and wait for the 3 cars to proceed until it merges in behind, because it can't reason about what the blue cars will do to let the yellow car in. So all games, in contrast, doesn't do this. The yellow car can reason that the blue cars will make way for the yellow car and open up a spot for it to merge. And so this is very practical, right? This is something that will allow autonomous cars to intelligently negotiate their motion with other vehicles. Okay, so all games, let's get into some of the details. So we have 2 varieties of constraints. We have collision constraints between vehicles. I'll just generally call these collision constraints. So no vehicle's circle can intersect with another vehicle's circle. And then we have road constraints. So no vehicle's circle can intersect with these white lines defining the boundaries of the road. So these are going to be the constraints in the problem when we're talking about a generalized Nash equilibrium. Then we have dynamics. Of course, dynamics are also constraints, but we're going to treat them a little bit differently. So when I talk about constraints, I'm going to specifically be talking about the road constraints and the collision constraints. The dynamics we deal with in the following way. So we're going to stack all of the vehicle states into one joint vector. This is more general because so in these multi-vehicle settings, it's common to imagine that each vehicle has its own state, and so its own control only influences its own state. That's fine. But in a more general setting, you can imagine that you have a more coupled dynamical system where every player has access to multiple of the states. So it's just more general to consider one joint state. You can consider this as the stacked states of all the vehicles if you want to think of a multi-vehicle setting. And then you have one player's control actions and other players' control actions. And this, I just haven't written all of them, but this can go up to n players. So we're just going to generically write this as a constraint inequality constraint, which is D for dynamics. Now the capital X here denotes the entire time sequence of states of the joint state. And the capital U denotes the entire time sequence of all the players' actions concatenated over time. So at any time, we take all the control players' actions and put them in one big joint action vector, and then we enumerate that through time. So that's capital X and capital U. Those are the decision variables in the problem, right? So, so then we can write the objective for a single player as, okay, J1, that's the player one's objective function subject to the dynamic constraints. and then subject to some constraints for collision avoidance and staying on the road pertinent to that one player. And then imagine all of the players have a similar kind of optimization problem. Now, I haven't put indices on the constraints, but every player can have its own set of constraints. That's fine. Just generically writing this as a kind of copied constraints. Now, the challenge here is that the constraints depend on the control decision variables U of, say, agent 1, but also agent 2, agent 3, and so on. So the coupling through the constraints is really challenging. So what do? We take each instance of this optimization problem. So we have all these coupled optimization problems. We take one instance and we append the constraints to the objective function using an augmented Lagrangian. So remember, JV is agent V's objective function, and then D is the dynamics constraints, and C is the collision avoidance constraints. So we have two varieties of terms here. So we have first a Lagrange multiplier for enforcing the dynamics constraints. We have a Lagrange multiplier for enforcing the collision constraints. So up to this point, this looks just like a regular Lagrangian, just the constraints times Lagrange multipliers, and that's fine. What makes it an augmented Lagrangian is that we have an extra quadratic penalty. And it turns out in all games, we've found that it works best to apply this extra quadratic penalty only to the collision avoidance constraints, not to the dynamics constraints. So we're dealing with the dynamics constraints with more of a standard Lagrangian technique, and then we're dealing with the collision avoidance constraints with an augmented Lagrangian. And these collision avoidance constraints are inequality constraints. We can also handle equality constraints, that's fine, but I'm just trying to keep it simple. So collision avoidance constraints being inequality constraints, this quadratic penalty, we want it to only apply when the constraint is violated, right? And so this I sub rho is a diagonal matrix where the entries on the diagonal are either active or not active. They're either 0 or rho sub k for the kth constraint. They're 0 if the constraint is not violated, or if this, excuse me, if the constraint is not active, and then they're rho if the constraint is active. So why do we do this? We do this because at the end of the day, we want to rigorously enforce the constraints, and the Lagrange multipliers are going to allow us to rigorously enforce the constraints, right? So exists some value for the Lagrange multipliers. If we bump up those multipliers high enough, it will cause the constraint functions to be exactly 0, and so we will satisfy those constraints. However, it's known, and we've found in practice, that if we don't, if we only look at the Lagrangian, we end up with numerical problems. This turns out to be a difficult problem to solve numerically. And so we add the quadratic penalty for better numerical conditioning. And I want to be clear that there's no approximation here. The optimal solutions, the minimizing arguments for the problem are the same whether or not you have the quadratic penalty, right? Because when the constraint is satisfied, the quadratic penalty goes away. So this is purely for numerical conditioning. Okay, so that's fairly standard, actually, dealing with constraint optimizations with an augmented Lagrangian. If you're fairly familiar with optimization, this is a fairly standard technique. So now what do? This is where we're actually talking about the algorithm, which is at the root of all games. So we take these augmented Lagrangians. For each augmented Lagrangian, we take the gradient with respect to the primal variables. That's the state trajectory and the control trajectories. And we're going to call that G. And then we stack all those G's into a big stacked vector of gradients. So now this is the composite gradient for the stacked system of all the augmented Lagrangians for all the players. And then we append the dynamics constraint to this gradient. So why do we do that? We do that because the dynamics constraint is exactly the gradient of all of the players' Lagrangians with respect to their mu Lagrange multipliers, the Lagrange multipliers on the dynamics. So all cars are responsible, all players are responsible for enforcing the dynamics. So there's no need for each player to enforce them separately. We just have a single, we just append to the gradient the dynamics constraint once rather than copying it m times for m players. It just cuts down on the dimensionality of the problem. So now we have one shared Lagrange multiplier mu that satisfies the constraints across all players, the dynamics constraints across all players. We haven't dealt with the collision avoidance constraints. Now we're only dealing with dynamic feasibility and then the optimization with respect to the primal variables, the state trajectory and control trajectory. Okay, so then we have this really big vector of the gradients. And then we take the Hessian of this thing. So we take the gradient of this big stacked gradient, take the gradient of the gradient to get the Hessian with respect to all the decision variables, including the duals, the mu's that enforce the dynamics. So we stack all these variables together, x, u, and mu. We call that y. So take the gradient of the gradient with respect to y, and we get the Hessian. That's h. This is a very large matrix. And then what are we going to do? We're going to apply Newton's method. So we have the gradient, we have the Hessian. So we're going to solve for a step direction in these variables, which are the x's, the state trajectory, the control trajectory, and the dual variables for dynamic feasibility. And we are going to apply this iteratively, right? This is Newton's method. So we take a beginning guess for these decision variables, and then we take a step in the direction suggested by Newton's method, and then we add that to the decision variables, and then we iterate, keep iterating until we converge. And there's a step size alpha, right? So this is pretty common for Newton's method, and we optimize the step size with a standard backtracking line search. So right, we don't want to step too far because we might overstep the local minimum, and we don't want to step too little because it'll take too long to converge if we take too small steps. So far, this is just Newton's method. Now let me talk about some details here regarding Newton's method. So the dimensionality of the problem I'm talking about is enormous, right? We have, m players. So maybe we have, I don't know, we'll talk about 2 players, and then we have the state dimension of each player and the control dimension of each player. And then we have the time history, the time horizon over which we're doing the plan. And these are the state variables, right? And so when we take the gradient of the objective with respect to these state variables, we get something which is the same dimension as the state variables, but then concatenated across all the players. So I'm talking about a very large problem that we're trying to do Newton's method on here. In practice, we don't compute the gradient, and we don't compute the gradient and the Hessian directly. We compute them through backward recursion, which looks just like a Riccati recursion from LQR, or iterative LQR, if you're familiar with this. So we do this kind of recursive back substitution, and this allows us to get this step direction, delta y. We get it, it's exact, right? This is numerically identical to taking the inverse of the Hessian and multiplying by the gradient, but we don't have to. It basically exploits the sparsity structure due to the fact that this is actually a dynamical system. It's much more efficient. Okay, so this is Newton's method. Again, I haven't talked about constraints other than dynamic constraints. So what happens when we solve this thing? If it converges, it's Newton's method, and we're talking about a non-convex problem, so it's not guaranteed to converge, but in practice, it always does. We have very, really strong convergence in practice empirically here. When it converges, what does it converge to? It converges to something that we are guaranteed to be dynamically feasible, but still may violate the constraints, the collision avoidance constraints and the staying on the road constraints, right? So this is where, so we have an inner loop, which is Newton's method, and then we have an outer loop, which is an augmented Lagrangian dual ascent. And this together is all games. Newton's method on the inside to get dynamic feasibility with a local saddle point, and then dual ascent on the outside to slowly, iteratively enforce the collision avoidance constraints. Okay, so all games, this is the whole enchilada, so to speak. We start by solving Newton's method, which gives us a trajectory for the state variables and the control variables for all the players, which satisfy dynamic feasibility, but violate the collision avoidance constraints. Then we do dual ascent on the collision avoidance constraint dual variables, that's lambda. There's a simple closed form, it's very simple to do dual ascent. You can see the details in the paper, the RSS paper, or the archive long form paper. And then what's standard in augmented Lagrangian methods is, remember, we have this quadratic penalty parameter rho, which lives on the diagonal of this diagonal matrix inside that quadratic penalty. And it's customary to increase rho according to a schedule. So a pre-planned, sort of increasing schedule that we've arranged beforehand offline. So then we crank up rho, we crank up lambda, and what we're basically doing is turning the screws on these collision avoidance constraints so that eventually they will be satisfied. And in the limit, through these 2 nested loops, Newton's method and then dual ascent, we end up with something which is dynamically feasible, and satisfies the conditions for a Nash equilibrium locally, so it's a local Nash equilibrium, and satisfies the collision avoidance constraints. And this is all games. So this, although it looks a bit fierce, this is actually really fast numerically. And it's also quite general, right? I've motivated this with drone racing and some freeway merging examples, but there's really nothing in here that I'm just talking about sort of general Nash style games. We can solve all kinds of Nash style games with this tool. So we can do ramp merging, as you've seen already. We can deal with intersection crossings with multiple different varieties of agents. The agents can all have different dynamics. So we can have pedestrian agents, and we can have bicycle agents, and we have car agents. We can deal with drones. So here's 4 drones passing through a window, and they would all like to go through at the same time, but the window is such that in order for them to avoid collisions with each other and with the window, they have to decide how to pass through one at a time. And so they solve for the generalized Nash equilibrium to do this pass through. And I already mentioned the frozen robot problem, right? So if you compare against a standard non-game theoretic MPC on the freeway merging, the robot is stuck, has to wait for the other robots to pass before it can merge. And we see this in practice, as I said, in around where I live. I don't know about this happens where you guys live, but you can see Waymo cars hanging out on the freeway, too scared to merge into traffic. Whereas in all games, we can successfully merge into traffic. Okay, great. So let's talk about some performance specs. Right, at the end of the day, we're talking about a non-convex game theoretic problem. And so there's not a whole lot we can say here analytically. We can say a few things, right? If we start close enough to a game theoretic equilibrium, to generalized Nash equilibrium, we can guarantee that we will approach that equilibrium because it's a Newton's method style approach. But beyond that, Newton's method doesn't have a lot of guarantees. We can converge to only a local Nash, not a global Nash, and we can converge to other spurious equilibria. It's possible. Although in practice, we find this really rarely happens. Okay, so how does this thing scale? So here you have 1, 2, 3, 4, 5 different systems with various sizes of state spaces and various sizes of input spaces. And we're solving this for these kinds of vehicles with this many number of players, right? So the thing I just showed you with the 4 quad rotors going through the opening, that's here. So it takes, looks like it takes about 3 seconds to solve that on a laptop computer, right? So that's pretty fast, I'd say, given that we have 12-dimensional state for each of the 4 players. And this is over a receding horizon over multiple time steps and a 4-dimensional input. Now, if you talk about problem setups that are relevant for driving, you have the bicycle and the unicycle model, 4-dimensional state, or with 2 control inputs. So those can be solved in a receding horizon fashion in real time. So you have up to 4 players here that can be solved in, looks like, what is that, 0.2, 0.3 seconds, something like that. So let's look at some performance comparisons against competing methods. So it's our belief that this is the only method that is appropriate for online game theoretic planning that really enforces constraints. That is, that really deals with generalized Nash equilibrium problems, with one exception, which I'll talk about in a second. Now, there are a variety of methods for solving for game theoretic equilibria, and many of them deal with constraints through a kind of soft penalty. So one of the popular methods, one of the methods that I think is quite nice, is called all games. This was developed in Berkeley by David Friedrich-Kiel, who's actually doing a postdoc in my lab right now. This was work with Claire Tomlin and several other students in Claire Tomlin's lab at Berkeley. And in this method by David, the game is essentially solved in an iterative fashion, similarly to the planning algorithm called ILQR, if those of you are familiar with ILQR. So ILQR, you take a general nonlinear planning problem and you linearize the dynamics and you quadraticize the cost, and then you solve an LQR solution. and then you take the controller from that solution, apply it to the nonlinear system and roll it out, and then you get a new equilibrium, a new trajectory, and then you again linearize the dynamics of the nonlinear system about that trajectory, solve solve the LQR again, and then again roll out, linearize, solve LQR, roll out, linearize, solve LQR. So those are the iterations in ILQR. We do the same thing for ILQ games. So you use the fact that there's a linear quadratic game solution in closed form with a Riccati recursion solution. You linearize the dynamics, quadraticize the objectives for all the players, and then you use the Riccati solution to solve for a game theoretic equilibrium there, and then you iterate just as I described. The problem is there's no way of enforcing hard constraints here. So instead what happens is you put the constraints in the objective as a quadratic penalty, and you hope to choose the penalty parameter so that they're nearly satisfied in practice. Okay, it's a very nice algorithm that has some pros and some cons with respect to all games. One of the main cons is the lack of being able to deal with constraints, whereas all games really does deal with constraints. In our comparisons, it seems that all games is faster. So you can see the performance here in various numbers of players with different scenarios. All games is solving faster in most of these instances. There's one exception here where all games is a bit slower. And you can see the timing here. This is clearly fast enough for an MPC loop, right? 38 milliseconds for 2 players, 50 milliseconds for 2 players, and so on. Now, I said that most algorithms cannot deal with constraints. All games can. There's one exception, which is this sensitivity enhanced iterative best response, which I mentioned at the beginning of the talk. This came from my lab. There are some real limitations with sensitivity enhanced iterative best response. Firstly, it only works with zero-sum games. It works great with racing. Racing is naturally a zero-sum game. But most of what I've talked about today actually for all games is non-zero-sum games. The freeway on-ramp situation, the intersection crossing situation, the situation where the drones are going through the window, those are all non-zero-sum games. And most, I'd say, human and human robot interaction scenarios are not zero-sum games. They're not overt competitions, right? So SEIBR is quite limited there. Nonetheless, we did compare performance between an IBR variant, iterative best response variant, which is widely used and very simple, versus our solver all games. And we find all games is just way faster, orders of magnitude faster. You see in these plots. So the blue line is all games convergence rate. The orange one is IBR convergence rate. Okay. So another issue that's interesting, that's relevant to generalized Nash-style games, which is the nature of the equilibria involved. So we've found in this problem setup that the Nash equilibria are not isolated. Typically, there's a whole manifold continuum of equilibria. And to understand that, you can see why. So if you look at the Hessian, so remember we have a Newton's method style algorithm, so we're actually computing the Hessian. If you look at the Hessian, we find that the dimensions of the Hessian are such that it has to be rank efficient, meaning there is a null space to the Hessian, which means that in a Newton step, once you've converged to the local Nash equilibrium by Newton's method, there are still directions that live in the null space of the Hessian, which preserve the local Nash equilibrium conditions, the first order Nash equilibrium conditions. And that indicates there's actually a manifold of Nash equilibria. We know this is true because the Lagrange multipliers that enforce a constraint like a collision constraint are copied. There's one set for one agent and another set for another agent. And each set of Lagrange multipliers lives as a column in the Hessian, whereas there's only one corresponding column for each constraint. So basically this is due to the fact that 2 players together are responsible for enforcing one constraint. And so what does this look like in practice? Can we actually investigate the manifold of the continua of Nash equilibrium? It turns out we can. So if you converge to a local Nash equilibrium, so first order Nash equilibrium, then you can actually march along directions in the null space of the Hessian, right? You can compute the Hessian, you can then find the kernel of the Hessian, and then you can decide to move to perturb the solution in a direction in the null space of the Hessian. And if you do that, and then it's going to leave the equilibrium. If you have a finite perturbation, then you have to project back, which is fine. So the idea is that we're kind of moving in the direction of the null space, we leave the manifold, and then we run a couple Newton's iteration steps to get back on the manifold. And in this way, you can explore this continuum of Nash equilibria. And what does it look like in, say, a driving scenario? Well, it looks like this. It looks like all the cars are trying to avoid collisions with one another, but that in that sort of collision avoidance configuration, you can, in a rigid way, move all the vehicles one way or the other and still satisfy the first order Nash equilibrium constraints. And this intuitively corresponds to sort of biasing the equilibrium towards one vehicle or another. So if you take this kernel of the Hessian and you explore the principal components that live in that kernel, you can see that they basically correspond to favoring one vehicle versus another. So if you kind of look here, the blue vectors are so how do I explain this? So the vectors in the null space of the Hessian are very high dimensional because they're the vectors representing the entire trajectory, the entire control and state trajectory of the vehicle. And so what you're seeing here is one of the principal vectors in the null space of the Hessian, but then projected at each of the coordinates of the vehicles. And so the blue is a principal component which favors the middle vehicle, because you see it spreading out the edge vehicles more to the side to allow the middle vehicle to proceed through the middle farther to advance its objective. Another of the principal components is these yellow vectors, and you can see that this is favoring this vehicle at the top because it's shifting these two guys down and enabling this top vehicle to ride along the center line, which that's its objective function, is to ride along the center line. So it turns out all games does something really nice, which sensitivity enhanced iterative best response, that's the only other method we're aware of that deals with generalized Nash-style games, does not do. So what all games does is it always finds a normalized Nash equilibrium, which is defined as a Nash equilibrium where every agent's Lagrange multipliers for a particular constraint are equal. The Lagrange multiplier is basically the price that an agent is paying to enforce a constraint. So if two players are responsible for the same constraint, using all games, they pay the same price to enforce that constraint. So no one player is at a disadvantage. There's an inherent sort of equity of the Nash equilibria that all games finds. And here's a visualization of this sort of manifold of generalized Nash equilibria that I was talking about. You can see what I mean. Kudos to Simon for sending me this figure this morning. He's of course the first author on this work. I think that really nicely explains how this works. Okay, so I was going to, if I had time, I was going to talk about inverse game theoretic planning. I don't have time. We have 1 minute left. But let me just motivate the idea, because I think this is a really interesting area for future research. So in all of the game theoretic problems that I've talked about here, and I suppose that we've probably talked about all day, we assume that there's one player who is using the game theoretic framework to predict the trajectories of all the other players and also to plan for its own trajectory, all in one solve, right? The problem is that assumes that the one player knows the objective functions of all the other players. And this is a little unrealistic, right? Especially in free form problems like in autonomous driving. How would I know what is the objective function of player A, player B, player C in trying to plan my trajectory with respect to those players? So in inverse game theoretic motion planning, we're inverting the problem. We're not looking at planning the trajectories of the vehicles. Instead, we're looking at observing the trajectories of the vehicles and identifying or learning the parameters of the objective functions of those vehicles online. And then we do this so that now we have a model of the objective function of the other players, so that now we can plan effectively with respect to them. So we have an algorithm that does that. I'm not going to talk through the details. It's called Lucid Games. It's appearing in RAL. I believe it's already appeared, and it's going to be presented also by Simon Lecleach at ICRA with the ICRA RAL pairing, right? And basically what this does is it uses an unscented filter to estimate the cost function parameters of the other vehicle online just by observing the trajectory of the other vehicle. And it uses all games, the solver I've talked about today, within the inverse game theoretic planning problem. So it basically says, okay, I have a bunch of hypothesis parameters for the objective function for that other player. I'm going to plan trajectories for myself and the other player, assuming these hypothetical parameters. And then I'm going to observe that other player's trajectory or partial rollout of trajectory. And then I'm going to score my parameters accordingly as which ones were more likely and which ones were less likely to give rise to that trajectory. And then I'm going to proceed with an unscented filter style approach. And what you're seeing here is those red dots are the hypothesis trajectories that the orange car has for the blue car. The orange car is the ego vehicle, the blue car is a human-driven vehicle. So the orange car is predicting the multiple different trajectories the blue car might take. And eventually those trajectories all converge to one when the orange car gains confidence on the parameters of that blue car's trajectories. And so this allows the orange car to predict that actually the blue car wants to avoid an obstacle and move into the other lane. Okay, so I had planned to talk about those details, but I don't have time. So I'm going to just go ahead and close there. So of course, I want to give credit to Simon, who's the lead author in all this work, and Zach Manchester at CMU, and to all of my partners in funding this work. And I want to point you to the GitHub repo, which has a Julia implementation of all games. You're welcome to check that out and try and use it. I appreciate all of your attention, and I'm very happy to take any questions. Thanks.
Thanks a lot, Mac, for the very interesting presentation. I just wanted to inform you that I think Simon is already answering some questions in the Google document. I think because
Perfect.
it's I can't see exactly who's typing, but maybe he can.
Thank you, Simon.
So I don't know. I leave it to Alessandro to manage. But if you think you can use a couple of minutes and you wanted to conclude what you were showing, you can also. I think there will be a few minutes for that. Would you like to do that?
Sure, I'm happy to do that. I don't want to derail the schedule of the workshop, though, and I want to give Alessandro enough time to give his talk. It's up to you. If you'd like me to, I'm happy to.
There's some time. So Alessandro's talk is in 15 minutes, and the questions are being answered. Alessandro, but you...
Yeah, please go ahead. I think it's no problem.
Great, I'll do that then. Great, thank you. So yeah, I already mentioned the setup here. So the orange car is the robot car, I'll call it the ego car, and the blue car is a human-driven car. So the orange car is trying to online predict the parameters, estimate the parameters of the objective function in a game theoretic context, like wrapped inside of a game theoretic solver. So the motivation is, as I said, the ego vehicle doesn't know what the other players are trying to accomplish. It does not know the objective functions of those players. What lane are they trying to stay in? What speed would they like to move at? And so on. Are they aggressive drivers? Are they passive drivers? So what we do is we wrap a parameter estimator loop around all games. And we find that all games is fast enough that we can simulate multiple hypothetical rollouts of the game, and then estimate those rollouts, the likelihood of those rollouts under different parameter values, and then use that to update the weights on those parameter values. So let's think about just having two players in the game. So the ego vehicle, the robot vehicle, is the orange one, the human vehicle is the blue one. Again, the problem is that the robot does not know the objective function of the human. It does not know J1. It knows the constraints. We're going to assume for now it knows the constraints. We'll say these are collision avoidance constraints, which ought to be apparent, or constraints to stay on the road, which should be apparent, right? And we make one fairly big assumption, but something that's quite common actually in the literature in inverse reinforcement learning or inverse optimal control. I should mention the context here. So the problem that I've described, if you take it away from game theory and just talk about this in terms of motion planning, right? So you don't have a game theoretic planning scenario, you just have a motion planning scenario where you have a robot looking to plan, or excuse me, a robot observing a trajectory and trying to understand the objective function that it came from. That's called either inverse optimal control or inverse motion planning or inverse reinforcement learning. You look at demonstrations of trajectories and try to infer the cost function that gave rise to those trajectories. That's inverse, as I said, reinforcement learning, optimal control, and so on. So to my knowledge, nobody's done this for game theoretic scenarios. And so this is what I'm proposing as a really interesting area to move into. So that's why I call it inverse game theoretic motion planning. And in most of this literature that is out there already for standard motion planning, it's common to parameterize the objective function, the unknown objective function, in terms of features and a weighting vector, a set of parameters, right? And so then we have a problem that's linear in the unknown parameters. Now, there are just starting to emerge some works in inverse reinforcement learning where we don't have this linear parameterization, but instead the objective function is just a deep network. So you have parameters of the deep network that are non-linearly tangled up inside the deep network, and it's those that we're trying to optimize. So in future work, we'll look at doing that because that gives a stronger representation power than what I'm talking about. But for now, we'll assume we have features, those are given, and some linearly appearing weighting parameters. And it's the weighting parameters we're trying to identify. And so all games works like this. It's essentially a UKF, an unscented Kalman filter. So we start with a Gaussian estimate, a Gaussian prior on the values of these unknown parameters in the objective function. Then we sample sigma points from this Gaussian prior. So if you're familiar with a UKF, this will be clear. If not, I encourage you to look up what a UKF is. It's pretty straightforward. So the idea is you have a Gaussian, and you can carefully pick a few points from that Gaussian. It's shown pictorially here. So for example, you take the mean of the Gaussian and then some of the points on the major and minor axes, the other principal axes of the ellipse of the Gaussian. And given these points, you can reconstruct the Gaussian exactly. So it's a small number of sample points that allows you to exactly reconstruct the Gaussian. Now, each of these sample points you consider, remember, these are points in parameter space. So each point represents a complete parameter set. And so these essentially represent a hypothesis about the parameters that the other vehicle is using. And now you can test this hypothesis, right? So you observe what that other vehicle is doing at the next time step. So let's say the current time step is xk minus 1. You observe xk, the next time step. You have your sigma points in hand, and you now roll those sigma points forward. You have one sigma point, another sigma point, all the way through 5 sigma points for the small problem, right? Each of these now becomes a trajectory hypothesis. And now you look at how similar the trajectory hypothesis was to the trajectory you actually saw at the next time step. And then you reweight the sigma points based on this likelihood, right? So the ones that are more likely to have given rise to the observed data, you weight with a large weighting, and the ones that are less likely, you weight with a small weighting. And now this weighted set of sigma points, you can invert to retrieve what's now a posterior Gaussian. So it's known in Kalman filtering, in the filtering literature, that this, for the linear Gaussian case, exactly recreates the Kalman filter. It's a exact sample-based implementation of a Kalman filter. And it extends directly to nonlinear, non-Gaussian cases, like we're looking at here. This is a nonlinear, non-Gaussian case. Okay, so then you end up with a posterior, which is again a Gaussian approximation on the distribution of the parameters. And the idea is that over iterations, this Gaussian will become smaller and smaller, more and more concentrated around the mean. And that means that you've done a better and better job at estimating the cost function of the other vehicle. So I'm just running the same simulation again, that now that has the ground truth trajectory of the blue vehicle. And then the smaller dotted lines are the estimate predicted by the robot vehicle. So you see first the estimate's kind of off, and then it converges to the ground truth. And then it's kind of off again, and then again it converges to the ground truth. This is because it's evolving online. Now I do want to emphasize how unusual it is to do online inverse optimal control, inverse reinforcement learning. Most of these methods use massive databases and they're solved offline. So really what we're trying to target here is the online solution in this game theoretic setting to be able to iterate in an MPC loop fast enough to do this in real time. And indeed, we find that we can do this in real time. So, so maybe Simon can talk to this, but I believe that the way we were able to get this speed, this is really impressive speed, I think, is through parallelization. So I think we're running every sigma point trajectory hypothesis in parallel on a different core in our multi-core processor. And so for 2 players, the expected time for one step update is 7 milliseconds. For 4 players, that's 87 milliseconds. So even for 4 players, we can do this in real time at 11 hertz for 4 players, or over 100 hertz for 2 players. What's interesting is we also have in hand an uncertainty quantification on our confidence of these objective function parameters, right? Now, the objective function tells us what the other car wants to do. The objective function tells us, does that car intend to stop? Does it intend to change lanes? Does that other car have an obstacle in front of it that we can't see, right? So we're actually able to take uncertainty into account. So we can plan for the ego vehicle to avoid the convex hull of trajectories that results from all of the sigma points in the filter, right? So if the sigma points are well spread out, they're going to lead to a set of trajectories that are quite diverse. And if we take the convex hull of those trajectories, we get a big mass of keep out region, which is illustrated in green here. It says, don't go into this keep out region because those are all possible hypothetical trajectories that this car could take. Let me actually, just trying to rewind this. Doesn't seem like I can do that. So if you'll notice at the very beginning, that keep out region is very large because the robot has no idea what the blue vehicle wants to do. You'll see it in a second. So here it's very big. So the robot has no idea what the green vehicle wants to do. And then it quickly collapses as we realize what the vehicle's intent is. And then we can proceed confidently. So we can do this kind of safety aware, chance constrained approach for game theoretic planning with this online parameter estimation. Okay. So now that is the conclusion of my talk with both the all games work for a fast online solution of generalized Nash equilibrium games for a variety of problems with drones or drone racing or cars or freeway on-ramps or heterogeneous vehicles, pedestrians, bicycles, and cars, and so on. And then I also talked about inverse game theoretic planning, where we're trying to estimate online the parameters of the other player's objective functions. Okay, I'm going to wrap up there. Thanks very much for your attention.
Thanks a lot again. Let's see if there's maybe a couple of questions, so we can still save the 5-minute break before we start. Well, I have a quick question, maybe. Yeah, so in the last thing you showed, it seems that you are kind of assuming that in the parameter space there's some notion of convexity or neighborhood or parameters which are close apart are actually describe similar situations.
Yeah.
But one would imagine that either the car is turning right or is turning left, and maybe there's a bimodal. I don't know if, and you don't want to be robust on the convex hull, right?
Yeah.
Is this something you have observed or not?
It is. Yeah, you're absolutely right. Yeah. So the filter that we've that I've talked about is inherently unimodal, and it will blur all those. If you have multiple distinct hypotheses in terms of turn right, turn left, it will blur all those together and become way overly conservative, right? So you'll end up with quite a spread out Gaussian that encompasses all the different discrete options, and that's obviously not ideal. So we're talking about, I shouldn't say we're working on, but we're talking about, and it should be relatively straightforward to implement a multi-hypothesis version of this, where you suppose there are multiple different Gaussian peaks in the uncertainty of the parameter space, and in fact the posterior in the parameter space is a Gaussian mixture model, and then you can update each of these Gaussian components with its own kind of UKF. It's a very good point and also very practical, especially in driving, where you do have these discrete decision points. So I think it's a really interesting area for future work, and we've talked about it, and we will work on it soon. And anybody else who wants to work on it, we'd welcome that, definitely.
Great, thanks. Alessandro, would you like to? Is there any questions you would like to carry over from the Google document, or there's a lot of great work in the document? It's a small monograph per se now.
No, there's maybe a follow-up question that got unanswered. For the rest was all good.
Sure.
So they were talking about the kind of equilibria that our games finds. Mm-hmm. And here I was saying, okay, it finds the normalized Nash equilibria, which are the ones for which you have the Lagrangian multiplier that are all equal. So in some sense, it's fair because it shares the penalties among all the players.
Right.
There's a question, the follow-up, which is does it hold also if there's no constraint violation? So what kind of equilibrium, I guess, if all the multipliers are, are 0, what kind of equilibrium?
Oh, right. I see what you mean. Okay, so if the solution doesn't require activating the constraints. So that's a great question. That is a great question. So in that case, I don't believe there's a notion of normalized. Like the notion of normalized Nash equilibrium is exactly a generalized Nash equilibrium where the multipliers are all equal for the same constraint. But in the case where the multipliers are not active, I mean the constraints are not active, still there could be a manifold of Nash equilibria, and then they're not generalized Nash equilibria, they're just standard Nash equilibria. And I think that's quite a difficult problem to characterize. I'll say, maybe Simon can correct me, but I think in our experience and the kinds of problems we've looked at, the Nash equilibria tend to be isolated unless the constraints are activated. If the constraints are activated, then we do have a manifold that we can prove. But in the case that the constraints are not active, I believe they tend to be isolated. That's certainly not a proof. It's not always true. One can show that sometimes there are still manifold of equilibria, but that's just an anecdote. Maybe Simon can fill in more precisely. Are you out there, Simon?
I think he cannot speak.
Oh, he can't speak.
Let me try to find him. I can promote him.
You can at least chat if I've said something wrong.
So he should be able to speak now.
Great.
Yeah. Can you hear me?
Yeah. Hi, Simon.
Yeah, this is exactly right, Mac. If you don't have active constraints, then typically the solution, the Nash equilibrium solution, will be isolated Nash equilibrium. But yeah, as soon as you have an active constraint, like a collision avoidance constraint, you may have like a continuum of Nash equilibriums.
Great, thanks.